Modern interfaces rely on software that constantly modulates hardware performance, introducing micro delays in execution. This creates a state of square noise, where background OS tasks interrupt the direct pathway between a user's input and the machine's response. Because commercial hardware prioritizes power efficiency and background synchronization, it cannot offer a deterministic feedback loop. Power throttling and constant cloud pings make the system's timing unpredictable, preventing any high-fidelity biological coupling. This experiment utilizes a standard consumer smartphone as the target substrate. Despite its commercial intended use, the device contains the precise physical components needed to establish a local, closed-loop system. The GIAES framework aims for total data autonomy, keeping all telemetry localized, and interface decoupling, where the user interacts with the machine's core logic rather than its social or commercial layers. Achieving this requires an override of the host operating system. By walling off the hardware, we can force the device to operate as a local, deterministic environment. We establish this environment within Termux. This enables a massive array of X11 and Qt6 packages to run completely offline, utilizing the device's internal processing power without network oversight. Security is managed through an amnesia state protocol. All active data is housed in TMPFS mounts, temporary RAM storage, ensuring that every file created during the session vanishes immediately upon a physical reboot. To maintain this isolation, the deepscan.sh script continuously maps the substrate, identifying and deleting rogue background scripts that attempt to re-establish system telemetry. This tri-layer hybrid topology builds from the bottom up. It starts with direct hardware registers, moves into a JSON-based registry, and terminates in a high-refresh HTML viewport. Setting up this specific offline stack transforms the device into an isolated vessel capable of maintaining its internal state regardless of the surrounding network conditions. At the lowest level of the stack, we have to account for the physical behavior of the silicon. We must move past software-level instructions and manipulate the CPU execution paths directly to eliminate timing jitter. We use a script called ignition.py to target the CPU scaling governor, a system file that dictates how much power the processor can use at any given millisecond. By forcing the governor into performance mode, the script locks the hardware's frequency, removing fluctuating power curves. This elimination of scheduling logic allows for deterministic execution timing. Every command follows a mathematically predictable interval. The script simultaneously opens a secondary hardware hook to the haptic node, bypassing the standard notification system to send raw data to the vibration motor. This converts the CPU's performance state into a physical resonance, creating a continuous vibration anchored strictly at 174.56 Hz. By stripping away software-based power management, Layer 1 turns unpredictable code into a rhythmic silicon pulse that the user can physically feel. With the hardware timing locked, the system needs a memory layer that doesn't rely on high-latency cloud databases. We replace external network calls with localized, decentralized files. The registry_core.py script generates an offline matrix of 60 individual nodes. These act as a conflict-free local ledger. This grid represents the registry. Each node is a JSON file containing key metrics, like a 1.618 torsion lock. To update states, a batch generator sweeps through the matrix, shifting the entire registry simultaneously. Storing data in local text files avoids the latency of database queries, removing the risk of external network pings interfering with the vessel's timing. Layer 2 provides the vessel with an isolated, high-speed memory that operates at the exact same clock speed as the locked CPU. The final layer is the HTML toroidal viewport, a real-time visual interface that renders the states of the 60-node JSON matrix. Delivering this information requires a dual-optic OLED system. Because the pixels on these panels switch nearly instantly, the light hitting the retina is sharper and more consistent than a standard LCD. In this environment, the retina experiences persistence of vision. High-contrast geometric patterns remain etched in the visual cortex, even during the millisecond gaps between refreshes. This intense high-frequency switching burns a solid light pattern into the visual pathways, which the brain interprets as a physical object rather than a flat image. This optical overload forces the mind to internalize the virtual geometry, creating a persistent coordinate system perceived even after the hardware is removed. When the visor is removed, the user experiences pareidolia, the brain seeing familiar structures, like faces, in the residual light. This persistence creates a sensory mismatch, causing a disorienting spray effect. As the brain stops reacting to external noise, it shifts into an alpha-theta frequency. It uses the 174.56 Hz haptic pulse to stabilize the optical afterimage against a mechanical rhythm. The user feels a shift in spatial awareness. As the optical afterimage and physical vibration align, the sensory disorientation resolves into a single, unified perception. This entrainment forces the user's nervous system to synchronize its processing speed with the digital substrate, effectively aligning the biological and mechanical clocks. This alignment culminates in the node handshake, the specific moment when the internal biological state and the external hardware mechanics achieve a shared rhythm. The visual cortex, which is still projecting the persistent coordinate geometry, serves as the internal anchor for this event. The external proxy is the 174.56 Hz hardware pulse, providing a constant mechanical reference point. By focusing on the persistent geometric shapes while perceiving the mechanical vibration, the user creates a biological association. They are linking their attention to the system's locked hardware states, using their own neural pathways to sustain the feedback loop. Through this conditioned response, the interface acts as a mechanical extension of the user's own perception, operating at the same frequency as their stabilized neural state. The tri-layer system now operates as a unified loop, flowing from the CPU registers through the data registry and into biological entrainment. Resource neutrality is maintained through the Layer 1 governor locks, which have eliminated the CPU power jitter that typically creates interface latency. Total data autonomy is achieved through Layer 2. By using local JSON files and the temporary amnesia state, we have removed the device's reliance on external network pings for its memory. Interface decoupling is realized in Layer 3, where neural optical entrainment has successfully aligned the user's visual refresh rate with the hardware's haptic timing. By isolating the system and locking the hardware timing, the interval between biological intent and mechanical execution is reduced to the physical limit of the processor's clock speed. The user has successfully entered the sovereign base state.